Works. First question, are there any non-Polish speakers here? Anybody? All right, so. I'm good, I'm fine, yeah, no worries. All right, so this presentation is about Apache Spark, about internals of Apache Spark. So if anyone here is not really familiar with the framework, I would consider going to the other rooms. Basically, because I will do like a very short recap of what RDDs are in Apache Spark and stuff like that. But what I want to do more intensively is go into the internals, how RDD is actually implemented internally, and then show you guys some code. So just a quick recap here. RDD, the definition stands for Resilient Distributed Dataset, right? Dataset because we have data in our cluster, is distributed because it's in the cluster, and the resilient parts is that you have the resilient built in within the API. So we have an example here. This is like very quickly recap. So probably, hopefully, something you guys already are familiar with. So we have a Spark context, which gives us a set of methods that give us this ability to fetch data from our system, from our cluster. Here, for example, I'm reading some logs from the HDF distributed file system. And then the thing that we get on the left-hand side is the RDD. Is the thing that we're going to work with when we use Spark API to do whatever calculations we are doing in the distributed environment. So we can do map, and that gives us yet another RDD filter, and yet another RDD if somebody might complain about performance issue. So we know that those operations are actually divided into two categories. One which will be called transformations, where transformations are lazy by nature, meaning that when you call that method, what you will actually get in the result is just yet another RDD. So it slowly builds your recipe for your calculations that are going to be run at some point on your cluster, while actions are other set of operations that once called will give you the concrete value, and those which are once called will actually trigger calculations on your cluster. Right? So far, so good? Like everybody is familiar here with the concept? Shout yay. Yay! You should be. If you're not, if that looks scary and weird and what the hell, then just seriously move to the other room. All right, so now the concept that not everybody's pretty familiar with is partitions. I mean, you can read about them on the documentation, but not everybody's really on like understanding what those are. So if you think of RDD as being a collection of your data within your cluster, partition is just a subset of that data. It's just a smaller subset of that bigger set of data that you have within your collection. So here you have an example where this is our data, this is our cluster built of 3 nodes here. So if RDD represents that big thingy here that we have, like whatever file that is, the partition is going to be just one small subset of that data. And when you, for example, calculate the count, so the number of lines within our text file, for example, the level of parallelism that we get from Spark essentially is working on an idea that you can divide that data set into smaller bits, into those partitions, and all of them can be calculated in parallel. So the level of parallelism that you get from Apache Spark is tightly coupled to the number of partitions that you have within your system. And those stuff can be calculated in parallel, and that's why Spark is so fast. Now the question would be here, right, because this is our pipeline, right? This is the thing that the ability to pipeline the calculation, the thing that we have running on our Spark cluster is called task. Now the question would be, what about this example? Like, we have some data, it's an old Shakespeare, so whatever Shakespeare wrote is in that file, and then we remove, let's say, empty lines. But what about the next step? When we group by the first letter of each of the line. I know we know what will happen next, right? When we do map values, all is good, right? This will run in parallel, this will run in parallel as well. But what's this thing in the middle here? Now the answer is that we're going to have this shuffle. So if we look at this example, this thing runs in parallel, this as well will run in parallel. However, all of those partitions at this point, they have to stop and wait for other guys to also return their values. So here you could just run in parallel independently. Each of the nodes could calculate stuff on each of the partitions and everybody is happy. However, at this point, you have to essentially stop and wait for everybody to finish their job. So then your data can fly around over the cluster, because this is the moment where data is just moving through your cluster using the network and just flying around to different parts of your cluster. So that's this bit over here is probably the most problematic when you have like really a lot of data and you have to do some stuff on it. And the rest after this we can run in parallel as well. So yeah, the last bit here, that from the Spark perspective, whatever can be run in parallel, Spark understands it as just a single calculation. You get the API that you can filter and map and group by and whatever, and this is a nice granularity that you get from the API. However, from the Spark perspective, what he sees in this program are just two calculations, which he calls stage 1 and stage 2. Because whatever he can run in parallel, for him, this is a single function that he runs. Like he can run on the single partition on a single node that can run in local one of the nodes running in your cluster. And because at some point the data has to fly around between your nodes in your cluster, this is the moment when it has to stop, and that's why he distinguished this as a single the first operation over here and the next operation over here. So that was a quick recap. Now the internals. So one more time, what is an RDD? We got this notion that this is distributed data set, awesome. And this is the notion that we get, which is helpful when you actually develop stuff. Like, we understand that RDD just represent this collection, and we have this notion that this collection exists on every other node and we can reuse it, right? But this is not how RDD is internally implemented. Internally, in order to have a running RDD, you need to have three things. One would be a pointer to its parent. Second one would be how internally data is partitioned within the given RDD. And the last bit is how to eventually evaluate internal data of that RDD. And we're going to look point by point before we see any code. So first, we're going to see how this question, how data is internally partitioned. So as you guys remember, this is just what I said just a moment ago, partition represents just a subset of data within our bigger collection, right? So one of the things you have to implement when you're implementing one of the RDDs, because, okay, maybe I should mention at the very beginning, RDD itself is just an abstract class, right? We have abstract class RDD. However, each of the methods, each of the transformations that you get gives you other concrete instances, concrete classes that inherit from that abstract class are called RDD. So you have, when you read from Hadoop, you will have Hadoop RDD. If you call map on your RDD, the next RDD you're going to get is map partitioned RDD. So there are different classes that inherit from that abstract class called RDD. So whenever you provide a new RDD, you need to implement few methods, and one of them is the information how that RDD should be partitioned. So the thing you have to implement is this method called getPartition. Get partitions, which essentially turns an array of partition, where partition is a trait, and that trait just holds a single information index. And now the question would be how that method is implemented internally. As it turns out, the implementation strictly depends on what kind of RDD you are working with. So just to put this sentence into perspective, imagine that we have Hadoop RDD. So we read some events from some journal here, and this gives us our RDD called journal. Another question would be how that, and this is the instance of this object here. The class of this object is Hadoop RDD, and now the question would be how Hadoop RDD is partitioned. If we were to implement this on our own, we could actually take leverage of the fact that Hadoop itself, the HDFS, the distributed file system that you have, is already partitioned. This is how the HDFS works. So if you have some file on your distributed file system, that file is already divided into smaller chunks called splits, right? So if this is your cluster, if this is your Hadoop instance, that split may live on node 1 by 1 and 2, this one as well, the next one, 1 and 3, and so on. So already your file on the HDFS is already divided into smaller splits, and the numbers of copies are correlated to the level of ways how you can deal with failures. But anyway, we could just take that information and reuse it to implement the getPartition method. So this is how getPartitions is implemented in Hadoop RDD. It kind of looks scary because there's a lot of code, but it really isn't. The most important part here is that we read the splits from HDFS that gives us the array of splits from HDFS, and then we create a new array which will hold partitions. The size of that array is exactly the same size of number of splits that we have in the HDFS, and then we just go, purely imperative code when we just iterate with for, and for each of the split, we create a new entry in the array, and this is what we return. We create an instance of partition, which is called Hadoop partition, and one of the things that that instance holds is the chunk, the reference to that chunk. So that's it. This is all that's needed to implement that for Hadoop. But the question would be, okay, Hadoop has already that implemented in it, right? The splits information. What about other RDDs? The next example would be map partitions RDD. So this is RDD that you get whenever you call things that normally they pipeline, like for example filter or map. Whatever is returned by filter or map, this is your map partitions RDD. Another question would be one more time, how map partitions RDD is implemented. Because we have like really small audience, can anyone give me a guess how that would be implemented? That operation here, when it reads stuff from HDFS, right? It reads that data from HDFS, and then it filters it, right? And that filter run in parallel. So we'll take your first chunk, filter some things from it. Here it will run in parallel as well. So what will be the structure of that next RDD? If you really think about it, the structure is going to be exactly the same. Because let's imagine that you have a Hadoop RDD with 10 partitions here, right? And then you call filter on it. So it will filter each of the partitions separately in parallel. So the next RDD you're going to get here will have the exactly same number of partitions because you never did anything to those partitions. You were just running that filter in parallel for every partition. You were just running that function. So to implement that method, all you have to do, we say like my partitions is inheriting partition information from its parent. That's the old implementation that you have to provide for map RDD. So take my parent, take his partitions, should be even called get partitions here, and just return it. Does it make sense? There's no point to recreating an additional number of partitions, setting a different value. You could just inherit that information that it will all work because it already runs in parallel. Next point is the parent. So we have this notion. All right, so this is the example of one of the things that you could do with Spark. Group by, map, filter, and take, right? But this is not how Spark sees your program. He ignores completely the lambdas internally because he cannot really do anything with that information. For him, it's just a bytecode that he has to deserialize and run. He cannot really do any assumption about the code internally running within your methods when you call your API. So essentially, the way Spark sees your code is exactly like this. This is all the information that he gets. So if we just move that call up from here, let's look how the example will work. Like we read some data from Hadoop, we group by, we map, we filter, and then we take. Now, at this point when we call take, the reference that we have is that RDD, right? So we have this notion that if we call take on it, in order for this thingy to be calculated, it needs to have some kind of notion of its parent. So if I am to filter some stuff, I need to know from which thingy I should filter that, right? So it needs to know where his parent is, because he will tell me, like, give me your data. And he'll be like, wait a minute, I have to ask my parent. And the next one will be, wait a minute, I have to ask my parent. And he's like, I have no parents, so I actually have to evaluate that data. So you ask that question to your very first ancestor, and then the data will flow the chart the other way, the other direction. So that's the notion we kind of have when we work with Spark. However, this is a little bit more complicated when you look at how it's implemented internally. So as it turns out, there are two kinds of dependencies that you have when you're talking about parents of your RDD. The first one would be called wider dependency. So wider dependency means that not only that I have a reference to my parent, but also I give you the information that the data, that when I will fetch that data from my parent, I will actually have to trigger shuffling. So whenever you have wider dependencies between two RDDs, you know at this point that this operation, retrieving that data from the parent, will require the shuffle operation on the cluster. The other set of dependency, which is called narrow dependency, doesn't have this effect. So it basically means that you can just read data directly from the previous parent partition, and you can run the whole thing in parallel. So these are the stages and tasks we've talked about before. So far, so good. I'm talking quickly because I want to have time to actually show you guys some code. So if you're fine with this, like if you have questions, just shout like, I don't understand that, this is stupid. Could you please speak in Polish or something? Just let me know. So the last thing here would be how to evaluate internal data, because I know how my data is partitioned, I know how to fetch my data from my parent, but if I don't have a parent, or if anybody asks me about my internal data, how to actually evaluate it. So now, so we know that whenever we call operations like collect, which are actions, this will eventually trigger the calculation on our Spark cluster, right? But now the question would be how those actions are implemented. And as it turns out, there's only one method that they always use, which is called run job. So you have a method on Spark context, which is called run job, and all actions reuse that method. So if you understand just that method, you understand every other action, how it's implemented in Spark. And run object takes, well, it takes 3 parameters, but the third one is actually not used that often. You will understand it once you understand those two. So I will just focus on the simpler version here. The first parameter is the RDD itself. So we want to run a job on some RDD, so you have to provide the reference to that RDD. And the next one is a function that takes the iterator of your type T, of whatever the T here is the type of the RDD, and gives you some value U. And the overall return value of that run job is the array of this U. So what that really means is that for the given RDD that you provide, Spark will take each partition. On each of your partition will call so partition holds the subset of data on your RDD, right? So it will take the iterator for each of the partition and pass that iterator to this function. So your function is going to be called, the many times you have, the number of partitions that you have is going to be exact number of how many times that function is being called, because it's going to call with each of the iterator for each of the partition. And I will just assemble the results U and put them into your final array U over here. So for example, how collect action is implemented. Collect action implemented is very easily. What we do is we just call the run job. We provide as the first parameter the RDD ourselves, because that function collect is implemented on the abstract class RDD. So we provide ourselves. And the function that we have to provide that takes the iterator for each of the partitions, well, essentially it will just change that iterator into array, right? So the final result is going to be array of arrays. And the last step is just to concatenate, flatten those results together. And you have your collect action implemented just by using this function over here. The other simple example would be method count, where count is even simpler. One more time, you provide yourself as the first parameter as the RDD, and the other one, which takes a function that takes the iterator and gives you some result. Here, our result's supposed to be long, right? Because this is going to be called for each of the partitions. So this is a util. I don't know why this is a util function. It could be just, take the iterator, call size on it. I will give you just the size of that iterator. So the overall result here is the array of sums. And at the very end, you just have to sum those results together, sum the array, which gives you the final long. That makes sense? Yes? Yes? No? Okay. All right, so the last thing here, the action take. I don't really want to jump into like details of how take is implemented because it didn't even fit on the slide. However, the important part is some people are sometimes they don't know what's going on with their Spark cluster because they run a single job. But instead of seeing in the Spark UI a single job running, they see 2 or 3. And they have absolutely no idea what's going on. They freak out. The thing is that you don't have the correspondence one-to-one. One action equals one job on your Spark API. And take is one of the examples. We see that takes actually is being evaluated in the while loop. And in that while loop, each time it calls the run job to calculate some part of data from the partitions. So if, for example, and that job you see in the Spark UI, this is the job that is being created here when you call that function. When you call that function run job, immediately you will see that information on the Spark UI. That's why when you have a take, for example, in your calculations, you're gonna see not one, but more like 2 or 3 jobs running. The last thing is the question, all right, I understand how run job is implemented. I understand that I have to provide that RDD. I understand that this function is going to be called on each of the iterators from partition. But who provides that data here, right? Who gives me that partitions and their iterator? And that's why we have to provide, that's why this last method here is implemented, which is called, you have to implement it, which is called compute. So compute is a method that you have to implement. It gives you that iterator here. This is the iterator that's going to be used as parameter to this function, all right? So you have to provide, you are responsible, if you develop RDD, you are responsible to implementing that iterator. So if, for example, you have, let's imagine Hadoop RDD, right? Where Hadoop RDD had that already that reference to that chunk in the HDFS system. This would be the place where somebody gives you that partition and you would implement it in a way, all right, so I'll just take it from that partition. I know this is a Hadoop partition, so I would just take a chunk, read that chunk from HDFS, that would give me an iterator, and I would just return that iterator. That would be the most naive way to implement the Hadoop RDD. But this is how it works. You just have to provide, you just have to tell us how to go from partition to data. And before we, just want to check how much time do I have? 15 minutes, not that much. So this is going to be quick. So I told you there are 3 things you have to implement to have the running RDD, which is true. But essentially there are 5. The other 2 are more sort of like optimization that you get from Spark. So RDD would essentially work with just those 3, but you can implement the number 4 and 5 to get a better performance of your RDD running in your cluster. So first one would be data locality. So as you guys remember, for example, in the HDFX example, when we had Hadoop RDD, and we were reusing that information from HDFS system to create partitions, right? If, for example, I want to calculate count on each of my partitions, and for example, one of my tasks is calculating count for, let's say, for this bit over here, which already lives on node 3 and node 1. But for whatever reason, Spark just sent a task where task is your calculations plus your data. So the count function plus your partition. And it will send to the executor which runs on node number 2. You get additional overhead, right? Because node number 2 doesn't have that data locally available. That data will have to be serialized either from node 3. This will still work. It will work, right? But the problem is that that data will have to be serialized either from node 1 or from node 3, travel through the network to your node 2, just to be calculated here and send back the results to master. It would be nice if Spark sent that work, this task to be implemented, to either executor which lives also on node 3 or node 1. So this is this data locality that you might have from time to time. And the way that we implement data locality in Spark is by implementing a single method, which I forgot the name. But anyway, the method, we can check it in a second. The method returns a string. And that string is just additional information for you to implement, which is that notion of information like, for example, you have Cassandra. Let's say you implement RDD for Cassandra. And you already know, all right, so this given partition lives on that particular data center on that particular node. So it would be a good way to inform, for example, push the IP address of that server or whatever, or host and something like that. The other one would be Partitioner. So that's the last element that you can, at this point, you don't have to implement when you provide when you implement your own RDD. And the Partitioner, the idea is simple. Let's imagine that you have two RDDs and you want to join them together. If you do, what you get is a full shuffling between those two, right? It only makes sense if you join two elements by a given key, and you end up with, so after the join, each of the partitions will hold all the data with the same key. So if I had like value here with key A and some value, and here key A with some value, they go into one place. And B's over here, and C's over here, and so on and so forth. So anyway, this data has to fly around the network, the cluster. However, if we have a little bit more complex example, that before we actually call join, the first thing that we do is we call group by some key here. So that data here is already partitioned by that key. You already have data with all the A's over here and all the B's over here and so on. And now you call join on them. So the thing that will happen is that here you still have to shuffle. The data still has to fly around the cluster. So all the A's will go here and all the B's will go, here and so on and so forth. But this thing is already partitioned. Actually, the algorithm will work the other way around. It will go like, listen, I already know my data is already partitioned. So instead of randomly moving the data around here, just try to move to correspond to the partitions I have already created here. Just reuse my partition information. The problem is and this is one of this was implemented in Spark 0 point something. Like was one of the first things that actually worked faster in Hadoop, and that's why they will actually be able to sell it to their customers. The problem might be the next step after you call group by is you call map. And now, if you call join on it, you get shuffling one more time. Do you guys know why that might be? Exactly, the key can change. Spark, as I said, Spark has absolutely no idea what you do here internally in those lambdas. For what he knows, you could actually change the keys. So that information can no longer be reused. And that's why you, for example, have map values, where the lambda that you're going to get is the lambda that actually get only access to the values, not to the keys. So then if you're going to call join on it, we can reuse the shuffling optimization one more time. But we have this notion, we see at this point that information about whether the RDD is partitioned or not, whether we called map, whether we lost that information or not, it traverses with our calculation. And this is how it actually is implemented. You have something which is called a partitioner, and then you have a method which is called getPartitioner. If that method returns null, it means there's no partition information available. So if you will call join on it, for example, like here, you will get a full shuffling. However, if that partitioner, if on that RDD you will call the getPartitioner and it will actually give you concrete object, then you can reuse its information. You know that that data is already partitioned and you can reuse that when you actually do the joins. Now I have 10 minutes to actually show you some bit of a code. If I don't make it, there's the repository is here. A nice thing about the repository is that the commits are like slowly graduated. So you can just go comment by comment and see the changes. And I have now 10 minutes, which is fine. Random RDD. So this is the simplest RDD that we can implement. The idea here is that we call on a Spark context a method random, and that will give us a random RDD, on which if we call take, it will just give us some random integers, right? This is the stupidest example that you can think of, but in the same way is the easiest one. So we can reuse everything we just learned for the past 30 minutes and see it in action. So the idea here is just to recalculate that and maybe just provide some additional information. For example, what would be the maximal size of things being generated, or the number of partitions that we want to have created with that RDD. So now, no worries, it's not going to be really live coding because I'm not stupid enough to do that. What I have is something which is called Git Time Machine, and this is so cool because I can just implement it with one click. This is how software should be implemented every time. So in order to implement RDD, what you have to provide here is you're going to extend from that RDD. And the RDD itself is the constructor is taking two, there are actually two constructors. Let's just focus on the default one. So it takes the Spark context as a parameter because it has to internally have that information of your running Spark context. And it also gets the list of the list of dependencies to your parent. Since we are creating the random RDD, which is going to be like the first RDD, so it have no parent, right? The list here is empty, so we just provide nil. And this is the normal constructor. So we take the Spark context, we push it to the super constructor, and the additional max size and number of partitions we're going to use in a second. So now we need to provide two functions here: the compute and get partitions. Those are required for this thing to compile. The get partitions is going to be quite easy because we will not really use any information from our partitions because we just randomly create data. But in order for this to work, we actually need to have partitions created. So here we just create an array of partitions, and we iteratively create in for loop, we just create a thing which we call random partition, where random partitions extends the partition, and the only thing that has to provide is the integer. If we, well, go away. If we would jump to Spark and see how partition, for example, is partition in Spark. This is the only thing that you have to provide here. So this index. And now the next thing that we have to provide is this compute function. And the compute function is going to be quite easy here. Not this. So the compute function. I'm just randomly. Do you guys see it like back there? So the compute function is implementing randomly generating for a given part. It takes the partition as the parameter, completely ignores it, and just creates some random data, puts it into the list, and then calls get iterator on it, and that gives him the ability to generate random information. As I said, the example is stupid because we are not using any information from the partitions, but it compiles, and you can actually see it running. I don't have time to actually call it, but you can believe me, if you run it, it will work. The idea here is maybe one more thing that we could provide. We could provide the implicit conversion. So there's a trick in Scala that you might, if you use this trick, the idea here is that you can provide for a Spark context additional method, which we call random, right? So the idea here is if you call Spark context.random, what it will do, it will just take your Spark context, wrap it up internally in the bytecode into this instance of this class, and gives you this additional method random that you can call on essentially on that object. So from the user perspective, wait a minute, where's my presentation? So from the user perspective, it looks like this. So it gives you this additional, because that method doesn't exist in Spark context, but since you have this conversion, you can actually reuse it. And just believe me, it works because I just wanted to go to more like a little bit more complicated examples. So here we have another RDD, which we call censorship RDD. And the idea here is that we have a list of strings, RDD of strings, and we want to have ability to censor any line that contains heresy, Hadoop, here in this example. So what we want to do is call censor on this RDD, and when we collect our data, it's actually not printed in the slides. Oh, crap. But anyway, the idea here is that if you get that information from that RDD, what you will get is the exactly same data set here, but all instances of word Hadoop will be changed to just asterisks, like, censor that word doesn't exist, something like that. So now let's, this might be a little bit more fun to see. Where is it? So this is the censorship RDD. All right. So this is how would we implement it. Now the difference here is that .rdd is not going to be the first RDD that we have. We're going to have some RDD of strings. It's going to be our parent, and from that parent we want to create that censorship RDD. So we're going to use a different constructor. I mean, sorry, we are still using. Well, we can use this first constructor. So this is exactly the same thing. We still need to provide a Spark context here as a first parameter, but we can read that information from our parent. Just take his Spark context and it will work. And the next thing that we have to provide is the dependency to our parent. Actually, it's a list. So we create something which is called one-to-one dependency. If we would look how the Spark is implemented, one-to-one dependency is just one of the examples of narrow dependency. If you guys remember the narrow dependency, which allows you to run things in parallel, this is one of those dependencies that actually, this is the narrow dependency that we've seen before. There's additional constructor that you could just call provide your parent into that constructor, and it will do that magic that we see before for you. So this is like a sugar here that you get from the API. Now, the getPartitions function, we're going to implement like taking that. We're going to take that information from our parent because we want to have those calculations running in parallel. If we have lists of strings and they are partitions and they are in different nodes, you just want to censor every partition independently. You want to censor this in parallel so that computation still runs in parallel, right? So you can reuse that information. You will just take from your parent the partitions and just returns it. The tricky thing is how you would implement the compute method. So now I have my parent. I need to censor that information from it. It will be just simple. Take the parent, call compute on it. So tell him like compute your data before I can do anything. It will give you for the given partition the iterator of those strings. On that iterator, you call map and censor the word Hadoop, so change the Hadoop with those asterisks, and return that iterator. And that's it. And it's all required for this thing to work. And the last thing that we can add is one more time this implicit conversion. So here the idea is that if you see RDD parameterized by string, then the user can actually call a method censor on it that will create a new RDD, censorship RDD, whose parent is going to be that RDD, right? So then you can reuse that function over here. So if you have a RDD of strings, you can actually call that method censor. And the last thing, just like a small issue that I might see, is that let's imagine that we want to right now implement an action. So we want to provide a function that it will be an actual, which actually trigger because that was transformation, right? It was just returning yet another RDD. Here we want to implement the action. We want to reuse that thing that we just learned about calling the method run job. So let's imagine we want to implement method collect legal, which for given list of, like for even sequence of strings, if it contains the forbidden word, it will just not be returned if you do something on it. Like if you actually, the list you're gonna get is just gonna be without the lines with the heresy. So implementing that will be quite easy. So we provide the collect legal function here. We're gonna call run job. So run job will trigger our calculations. You gotta remember, we're gonna provide the RDD is gonna be ourselves. So we just provide this. And the function here, the lambda that we need to provide is just for given iterator, filter out all those who contained the heresy here. So Hadoop at this point, and just change it to array, concatenate those results, and return it as a final array. Now the question would be, will that work? You guys think it will not, but the question is why not? I know I've been running because there was a lot of material to cover, and I probably lost you right now, guys, but the idea was here that this function, when it's going to be called, it's going to get data from somebody. right? That iterator, the parameter here, will be provided by this compute method. And what is compute method doing to Hadoop? It's changing that to the asterisk here. So if you're gonna filter by Hadoop, that Hadoop is no longer exists at this point, right? It doesn't exist at this point. So if you try to filter out the results, the Hadoop word doesn't exist. So this will actually not work. The implementation that would work would be a stupid implementation where you provide yet another field here called mask, and then you would filter out by this mask. So instead of filtering like before, instead of filtering by the heresy word, you would filter out by the mask, which is obviously stupid, because if you have a line which just holds by some weird coincidence 6 asterisks, it would also be filtered out at this point, right? But just the idea about the example was to just show you how those two methods are correlated, because the data that you're gonna get into that iterator is provided by the computer function. So if you do something to your data here, just beware that it's actually going to be reused at this point, as we see in this example. Now, before I finish, the question would be, why even care? There's not really that much point about caring implementing your own RDDs. I mean, there are situations where implementing your own RDD actually makes sense, but it's not really that common. The cool thing about it, and the idea here about this presentation I was hoping to show you guys, was that seeing how, I didn't have time actually to show you the internals of RDD, but seeing how Spark works internally, like browsing the code base, is nothing more complex than what I just showed you. And just knowing how that works internally, knowing this about the thing about compute function, it might, the examples that I show you are quite easy, and you might wonder why do I should even care. But just having ability to understand how Spark works internally can save you tons of times when something fails on production and you get some weirdest exception that you can ever imagine, and have this knowledge to actually know, all right, I know what that means, because actually seeing it in the code base is really, really beneficial. So if you work with Spark, I strongly encourage you to play around, like write the RDD for fun and profit, because it might be a little bit of fun, and at some point you're gonna get that profit, and that profit is gonna be your sanity when your cluster is red and everybody is screaming, especially your boss, on you. That's pretty much it. My name is Paweł Szulc. This is my email, my Twitter, my blog, and if you're interested in those examples, this is the link where you will have a link to slides and also the code. And thank you very much.